Hello and welcome to my YouTube channel. In the previous lecture, we have discussed about Fermi Dirac distribution, why Fermi Dirac distribution is important when we study semiconductor devices or semiconductor physics, and what is the application of Fermi Dirac distribution in semiconductor physics. Now in this lecture, we are going to discuss about Fermi Dirac distribution and its application in different types of semiconductor. So without any delay, let's start the video. First of all, let us talk about intrinsic semiconductor and how we can establish some relationships with the Fermi Dirac distribution in case of intrinsic semiconductor. Intrinsic semiconductor represents pure semiconductor, and pure semiconductor has equal number of electrons and holes. So in the previous lecture, we saw that Fermi Dirac distribution is shown as shown in the graph. In the x-axis, we have f of e, which is nothing but a probability distribution. Okay, it is nothing but a probability. So the range of f of e lies between 0 and 1. Whereas in the y-axis we have energy, that is the energy associated with the electrons or any charge carrier. On the right side we can see the representation of conduction and valence band, where EC represents the energy associated with the conduction band and EV is the topmost energy associated with the valence band. And in the previous lecture, we also saw that in case of pure semiconductor, the Fermi energy EF always lies in the middle of EC and EV, assuming that the effective mass of electron is equal to effective mass of hole. In that case, we can say that EF, that is Fermi energy, will be in the center of EC and EV. Now let us go a bit deeper in the graph represented here. So f of E, the probability function, ranges between 0 and 1, 0 representing 0% probability and 1 representing 100% probability, and 1 by 2 here represents 50% probability of finding an electron. For a pure semiconductor or an intrinsic semiconductor, the probability of finding electron with an energy EF or with an energy less than EF is almost 50%. Therefore, we can see here that finding an electron with an energy EF is 50% in case of pure semiconductor, because it has got equal number of electrons and equal number of holes. As we move up in the conduction band, okay, remember we are moving to the higher energy band when we move upward or above the EC. So as we move up, the probability of finding electrons are decreasing. Suppose here it is representing 10%, then in that case, as we keep on moving higher, we will find lesser and lesser number of electrons in the conduction band. That means the density of electrons will be very high near the EC. So as you move up, the density will keep on decreasing. So let us assume this is the representation. Okay, so as we keep on moving up, we will find less and less number of electrons in the conduction band. So the density keeps on decreasing and the probability of finding an electron in the higher energy bands will be very less, or finding an electron higher than EF, energy EF or energy Fermi energy, will be lesser and lesser as we keep on moving up in the energy band. And when we keep on moving less than or below the EF, Okay, that is, here we have lower energy. So in that case, here it is representing somewhere around 90%. So as we keep on moving downward, the probability of finding charged particles will keep on increasing, or energy of electron less than EF is always 100%. So from this graph, we can say the holes in the valence band are the vacancy created by electrons that have been thermally excited to conduction band, as opposed to the doped semiconductors where holes and electrons are supplied by foreign atom acting as an impurity, or we can call it doping. Okay, so the more the energy you apply externally to the semiconductor, so suppose this is external energy, and what are the different energies that we can apply? We can apply light, we can apply heat, or we can even apply pressure. So as we keep on applying external energy, and if that external energy is greater than Eg, which is the energy band gap, the electrons will move to the conduction band, leaving behind holes in the valence band. So the more the electrons move to the conduction band, the more holes will be generated in the valence band. This is in case of intrinsic semiconductors. Now coming to the extrinsic semiconductor and taking an example of p-type semiconductor. Remember, p-type semiconductors have more number of holes in them. Why more number of holes? Because in this case we take the fourth column elements, which are semiconductors, and we add them with third column elements, resulting as p-type semiconductor. And when we add 4 plus 3, it becomes 7, whereas we need 8 electrons to make it stable. So therefore we end up with an extra hole. So the more the number of impurities from third column you add, the more the number of holes will be generated. And as we keep on adding the third column elements with the pure semiconductor, we make the device more and more p-type. Now what will happen in case of p-type semiconductors, and where the Fermi energy will shift in case of p-type semiconductors? So here we have again Fermi distribution between 0 to 1. The more the number of holes generated, the more the EF or Fermi energy will move away from the conduction band, or we can say the EF moves closer to valence band. So in case of p-type material, the Fermi energy level moves closer to the valence band. So the impurity that we generally use in case of p-type semiconductor are from third column elements. One of the example is boron, and we can add with silicon, which is pure semiconductor, and boron comes from the third column elements. And the more the number of third column element we add, the more number of holes we will generate, and holes will always try to accept electrons. Therefore this term acceptor appears in case of p-type semiconductor. So in case of p-type semiconductor, we will have more number of acceptors. Acceptor here represents they accept electrons because they are holes, and they will wait for an electron to recombine with them. So these are called acceptors also. Okay, acceptor atoms. When the acceptor density is increased, the Fermi level moves closer to the edge of valence band. So if you keep on increasing the impurity in p-type material, the Fermi level moves closer and closer to the valence band. So remember, in case of p-type semiconductor, the EF moves closer to the valence band. Whereas in case of n-type semiconductor, for making n-type semiconductor, we take the fourth column elements, which are basically pure semiconductor, and we add them with fifth column elements. Okay, we can call them pentavalent, and this gives rise to 9 electrons. Okay, whereas the semiconductor can hold only 8 atoms in the outermost orbit. So one extra electron is generated in case of this kind of combinations, 4 plus 5. So the more the number of pentavalent elements are added, the more the number of electrons will be generated. So higher the impurity, higher the number of electrons in case of n-type semiconductor. And we can see all these electrons are arriving more to the conduction band, and therefore the Fermi energy EF shifts more closer to the conduction band. Okay, and here you can see the probability of finding electron is more close to the conduction band. So from this we can say that when donor density, not why we are calling them donor, because we have an extra electron which can be donated to any hole or nearby hole of any other semiconductor. So these are called donors because we can donate electrons. So when the donor density increases, the Fermi level moves closer to the edge of conduction band. And to make p-type semiconductors, we generally use elements from fifth column, for example arsenic, and we add them with pure semiconductor like silicon. So two things we have to remember in p-type semiconductor. Okay, the conduction EF moves closer to the valence band, and in case of n-type semiconductor, EF moves closer to the conduction band. Now, what about the electron and hole concentration when the semiconductor is kept in equilibrium? Remember, equilibrium is achieved when, or we can say a semiconductor is in equilibrium when there is no change of temperature, pressure, or doping is applied to the pure semiconductor, or we can say it is in steady state condition. So the number of electrons and number of holes will remain same and they are not changing with respect to the environment. In such case, we will call that the semiconductor is at equilibrium. So what will happen to the holes and electrons when the semiconductor is at equilibrium? So from the Fermi Dirac distribution or Fermi Dirac distribution function, we can calculate the concentration of electrons and holes in semiconductor, provided we know the densities of available states. So that means the density of holes or density of electrons. If we know the density of holes or electrons in the valence and conduction band, then we can find the probability of, or we can easily find the probability of Fermi Dirac distribution. The concentration of electrons in conduction band can be given by N naught under equilibrium. Naught is representing the equilibrium condition. Okay. So number of electron under equilibrium is given by the integration of EC to infinity f of E n of E dE. How we can interpret this equation? Here NEDE is the density of states per centimeter cube in the energy range dE. So let me draw just a centimeter cube. Suppose we have a semiconductor. This is a 3D representation. If I have a semiconductor, in that case, if this is 1 centimeter cube, 1 cm, okay, 1 cm and 1 cm. So if it is 1 centimeter cube, then if we take small chunks of these semiconductor, okay, then we can call this height dE, okay, and in this region or in this volume dE, how many electrons are available? If we keep on adding such dEs, okay, throughout the semiconductor, then we can say what is the density of electrons in this whole semiconductor. So to find the concentration of electrons in conduction band, we have to integrate the, suppose here we have the EC, we move upward towards infinity in the semiconductor, okay, to find the density of electrons. So if we keep on adding all these small chunks of dE and add them together, because it is an integration from starting from EC to infinity, we will get the concentration of electrons. Therefore, the number of electrons per unit volume is the integral over the entire conduction band. Yes, it is obvious that if we add all the electrons starting from EC, okay, here suppose it is EC, upward till infinity, this is our conduction band, okay, then we will get the concentration of electrons in the conduction band. Now let us talk about density of states or Fermi Dirac distribution and the carrier concentration of intrinsic semiconductor. Remember, again we are talking about here intrinsic semiconductor, and we are going to correlate density, Fermi Dirac distribution and carrier concentration for pure semiconductor. So for pure semiconductor, the number of electrons and the number of holes will be always same, and the concentration of electrons will be very high near the EC, and as we move upward the concentration keeps on decreasing, okay, or the density of electrons decreases as we move up in the conduction band, and same is the density of holes decreases, okay, as we move away from the EV. So highest density will be near the edge, whether you are taking the conduction band or valence band. So if we try to plot the Fermi energy with respect to conduction energy band and valence energy band, then let us assume there are three lines: the brown line representing conduction energy, green representing valence energy, and EF representing the Fermi energy. And in case of semiconductor, we have seen EF will be at the center of EC and EV. Now, if we correlate the Fermi energy diagram with the conduction and valence band, then we can see that as we keep on moving upward, the energy, as we keep moving upward, the density of electrons keep on decreasing. So here we have very high density and when we keep moving upward, the density becomes lesser and lesser, okay, or the energy associated with the electrons keep on decreasing. So if we further go to the density and Fermi energy, and if we integrate these two region, for example the region which are represented by the square boxes, okay, then if we integrate these two regions, then we will find that the electrons, okay, near the conduction bands have higher density, and as we keep on moving upward, the density keeps on decreasing, and the energy associated with the electrons also keep on decreasing. So all the electrons, we can say, will be near the EC, here in the EC region. Similarly, maximum number of holes will be near the EV. This is in case of intrinsic semiconductor. So if we integrate these two regions, okay, if we integrate these two regions, then we will end up with a distribution as shown in the graph, okay, for the holes and electrons. So in case of intrinsic semiconductor, these distributions are same. Now let us take an example for extrinsic semiconductor and n-type semiconductor. We know that in n-type semiconductor, we will have more and more number of electrons and less number of holes. Now if we correlate the Fermi energy, the Fermi energy in case of n-type semiconductor is shifted close to the EC that we have seen from the previous slides. Now if we correlate the energy band diagram with respect to the Fermi energy levels distribution curve, then we can see the energy has been shifted, or EF has been shifted upward close to the EC. And if we further bring the density curve, here remember Ne is representing the density of charge carriers, be it hole and electron. So if we integrate this region with the density region, then we will end up with this curve where we can see the electrons density is very high near the conduction band, whereas in case of holes, we have seen that in n-type semiconductor, holes are very less, okay, and those holes are very close to the EV. So if we integrate these two regions for n-type semiconductor, we will find a distribution which is much lower than the distribution shown in for the electrons. So in the electrons, we have a higher concentration level, whereas in holes we have very less concentration level, and this curve represents the relationship between density of states, Fermi Dirac distribution, and carrier concentration for n-type semiconductor. Because it is n-type, the curve for the electrons will be much larger, and as we keep moving upward in the energy diagram or towards the higher energy level, we will find lesser and lesser number of electrons, because all the electrons are concentrated near the EC. As you keep on moving upward, you will find lesser and lesser number of electrons. Now taking the example, okay, before that, let us conclude this slide. So that means the Fermi function becomes extremely small for large energies. So if you keep on going upward for larger energies, the Fermi energy becomes extremely small. This is true from the distribution that we have seen for the electrons in the curve. Secondly, the result is that the product F of E, N of E decreases rapidly above EC. So if you move upward in the EC region, the function F of E, N of E, okay, rapidly decreases, and very few electrons occupy energy states far from the conduction band edge. Here is the conduction band edge, And if you keep on moving far from the edge, the electrons that occupy higher energy level are very, very small. So this is the relation that we can extract from these three diagrams. Now coming to the case where we have extrinsic semiconductor of p-type and try to correlate density of states, Fermi Dirac distribution and carrier concentration for p-type. So here in p-type we can recall that p-type semiconductor we will have huge number of holes and very few number of electrons, and we have also seen that the Fermi energy moves closer to the valence band. So if we draw the lines for EC, EF and EV represented by brown, blue and green lines, then let us correlate again the Fermi energies function. We can see that the Fermi energy has been shifted from center KEF has been shifted close to the EV or valence band because you have more number of holes near in the valence band. And if we correlate that with the density of electrons and holes, okay, Ne is representing the density. So in that case, if we integrate this region and this region along with this region in the bottom near the valence band with the density of valence band, then in that case we will end up with the distribution shown in the last diagram or the rightmost diagram. Here we can see the distribution of electron is very less in case of p-type semiconductor. Yes, because there is very few electrons in the p-type semiconductor, whereas in p-type semiconductor where we have huge number of holes and maximum holes are concentrated near the EV region, and as we move away from the EV region we will find less and less number of holes in the valence band. Therefore this distribution is much larger than the distribution of electrons. That means distribution of holes is much larger than the distribution of electrons for p-type semiconductors. So we can say the probability of finding empty state or hole in valence band decreases rapidly below EV. We can see here when we move below EV, the density of holes rapidly decreases and it is highest near the edge of EV, and most holes occupy the state near the top of valence band. Yes, we can see from the distribution most of the holes are near the top of valence band. With this I would like to end this lecture or presentation. If you have any doubts or suggestions or comments, please share your doubts, comments and suggestions in the comment section. If you have any recommendations for me to improve the videos, please do share your recommendations also. If you have not subscribed the channel, then I would request you to please subscribe the channel and share this video with your friends. Thank you and have a nice day.